In this video, we are going to learn how to solve the 0-1 knapsack problem. It states that given a knapsack with maximum capacity W and a set S consisting of n items, each item I has some weight Wi and benefit value Bi, where all Wi and capital W are integer values. The problem is to find how to pack the knapsack to achieve maximum total values of packed items. Let us take an example to understand what a knapsack problem is. Suppose we are given 3 items. Each has got some weight and some benefit value Bi. We are also given a weight capital W, let's say equal to 10, which is the maximum capacity of the knapsack. So our problem is that we have to find that using these items, how can we pack this knapsack such that we are able to pack maximum benefit value in maximum possible weight. Therefore, our task is to find the maximum of summation of Bi values subject to summation of Wi such that it is less than capital W, that is the knapsack weight. The problem is called 0-1 because each item must either be entirely accepted or rejected. That is, we cannot choose an item in fractions. To solve the problem, first we look at the brute force method. In it we go through all combinations and find the one with maximum value and with total weight less or equal to capital W. Running time will be of order 2 raised to the power n. Next we define the subproblem. Let's say that the items are labeled from 1 to n. Then a subproblem would be to find an optimal solution for Sk, where Sk represents a set of items labeled from 1 to k. This forms a reasonable subproblem definition. But the question is, can we describe the final solution in terms of subproblems Sk? Unfortunately, we can't do that. Let's understand why we can't do so by an example. Suppose we are given Wi and Bi values for 5 items, as you can see in this table. Let the maximum weight of the knapsack be 20. Now for S4, maximum benefit comes out to be 20 for a total weight of 14. The items we choose for S4 are 1, 2, 3 and 4. Now let's look for S5. For S5, the maximum benefit comes out to be 26 for a total weight of 20. The items we choose for S5 are 1, 2, 3 and 5. Clearly, solution for S4 is not part of the solution for S5, as we have not taken S4 as a part of the answer of S5, because including item 4 would have exceeded the knapsack capacity. So what to do? How do we solve the problem? Let's redefine the solution. We add another parameter W, which will represent the maximum weight for each subset of items. The subproblem then will be to compute VKW, that is to find an optimal solution for Sk in a knapsack of size W. Now let us look at the recursive formula for the subproblems. This shows the recursive formula we are going to use to solve the problem dynamically. It states that if the weight of the kth item is greater than the maximum weight for that particular subset, then choose Vk-1, W, else choose maximum of Vk-1 W or Vk-1, W-Wk. The formula is further explained as follows. It means that the best subset of Sk that has total weight W is the best subset of Sk-1 that has total weight less than or equal to W, or the best subset of Sk-1 that has total weight less than or equal to W-Wk plus the item k. So the first case here means that if Wk is greater than W, then the item k can't be part of the solution, since if it was, the total weight would be greater than W, which would be unacceptable. The second case states that if Wk is less than equal to W, then the item k can be in the solution, and we choose the case with greater value. Next we look at the algorithm. We begin filling the VKW table by first initializing the first row and first column to 0. For the rest of the values, we use the formula we just studied. Let us take an example to understand the algorithm. Let n be equal to 4, meaning that there are 4 elements present. Let the maximum weight of the knapsack be 5. The elements with their wi and bi values are these. So this is the VKW table. We fill the first row with all zeros first. Then in the next step, we fill the first column with all zeros. Then we finally begin filling the rest of the values of the table. Now I is equal to 1, representing the first item of the list. It has got bi value equal to 3 and wi value equal to 2. The first w we choose is 1. W minus wi becomes equal to minus 1 because 1 minus 2 is minus 1. So what does our algorithm say? It states that if wi is less than equal to w is 1 and wi is 2, this condition becomes false. Hence we skip to the else part. It states that v of iw is equal to v of I minus 1 comma w. Hence v of 1 comma 1 becomes equal to v of 0 comma 1, that is 0. Next, for w equal to 2, this condition becomes true as wi is 2 and w is also equal to 2. Now let us look at the second condition. It states that if b of I plus v of I minus 1 comma w minus wi is greater than v of I minus 1 comma w, then set v of iw equal to b of I plus v of I minus 1 comma w minus w of I. So bi is 3. v of 0 comma 0 is 0. Therefore we add 0 to it, which is greater than v of 0 comma 2, that is 0. Therefore we set v of 1 comma 2 to be equal to 3 plus 0 equal to 3. Now pick a pen and paper and complete the table using the algorithm. The final result we get, that is the maximum benefit value, is 7 for the given set of items.